Okay, welcome to the morning session of Wednesday. Today's speaker, the first speaker is Subhadip Dey, who is going to tell us about irreducible discrete subgroup of G times Z and ergodicity of the boundary.
Yeah, thank you so much for being here, and thanks to the organizers for inviting me to this nice conference celebrating Mises mathematics. We all know, like, it's not a secret that he has like large interest like in various topics in mathematics. So in this talk, yeah, I'm probably going to talk about a small portion of it. So the title is Irreducible Discrete Subgroups of Z times C and ergodicity on the boundary. So it's a joint work with Sebastian Gupta. So I'll start with one question that I had from Misha, and he also wrote it down in a list of problems he wrote like recently, compiled recently. So the question is, so suppose we consider the group, let's say gamma, which is SL3Z. So this is a lattice in SL3R. Okay. Yeah, the question is about trying to understand how subgroups of this thing look like. Okay. So so surprisingly, all known infinite index subgroups. Okay, there are a lot of finite index subgroups and their lattices, but I think it's more interesting to ask like what kind of infinite index subgroups we have here. Okay. Quite surprisingly, that we don't know too many examples, and all examples which are kind of discrete here are surface groups or free groups. Okay, so give an example of an infinite index finitely related subgroup which is not a surface group, which is not virtually a surface group. Or free group. Okay, so by surface group I always mean it's the fundamental group of a closed hyperbolic surface. Okay. Okay, so for example, yes? Yeah, I'll consider Z square as an exception.
So maybe you don't want to stay hyperbolic on your surfaces?
I couldn't see. What?
Maybe you don't want your surfaces to be hyperbolic.
Closed hyperbolic? Like, okay. Closed surfaces with orientable, with genus. So whenever I say surface group, it always means this. Okay. Oh, sorry, I'm writing too small. Okay. Closed surfaces which are orientable and with genus at least 2. When I say surface group, I always mean this. Okay? Yeah, I'll consider Z2 as exception. Exceptional surface group. Okay. Yeah. Yeah, otherwise I have to make this comment every time I write surface group. Okay. So for example, can we embed this group or this group inside SL3Z? And as you can see, I'm clearly kind of distinguishing that this is not of this kind. Okay. Any question? Looks good.
Sorry,
Yeah.
I do have one more. Are there known examples of, so there are known examples of hyperbolic surface subgroups by subgroup?
Yes, there are known examples of. So, yeah, I kind of forgot the history, but I think one of the earlier ones are constructed by Feinberg. But there are some explicit examples constructed by Long, Reed, and I'll most probably misspell this name, Tisselwhite. Yeah, I think I'm misspelling this name. But these people, they constructed closed surface groups. Okay. And one can actually make also these examples discrete. So you. Oh yes, yes.
Not just the small things.
Yeah. Okay. Okay, I'll try to write bigger. Okay. Okay. So what is kind of the motivation for this question is this old question of Said. Which asks if this group is coherent. Is it big enough? No? Okay. Is it better? Okay, good. So what is coherence? So a group is called coherent if like all finitely generated subgroups are also finitely presented. Okay. So the question is whether this group is coherent, and to understand this question, like we need to at least know some nice examples of finitely generated subgroups, right? If the list is just surface groups and free groups, then yeah, it's kind of difficult. Okay. Okay. Actually, one can generalize this question that we have there. So maybe this is question 2. So let's take this example. So does there exist a discrete and faithful embedding of this group inside SL3R. So you're enlarging the target, and we're asking whether you can put this discretely. Okay? And this is also not known. This makes sense? Okay. On the other hand, like if you look at the other example, so this is like part A. So for the second one, so maybe this should be remarked. So there are examples of discrete embedding of this group inside this bigger group. So there exist. And these examples were constructed by one of Misha's former student, James Forehand, and it was also found by Soifer. Okay. So the idea is like, okay, it kind of uses ping pong argument. Okay. So basically, one has to find a nice Z2, when you can kind of apply some kind of ping pong argument. And the problem with the smaller group is that there is no nice Z2 like this in that one. Okay. So more specifically, one needs to have this generated by some diagonalizable element which has 2 equal eigenvalues. But SL3Z doesn't have those. Okay. Okay. Okay, so in general, it's hard to construct interesting families of discrete groups in lower dimension, especially in lower dimensional Lie groups. So for this talk, I'll not talk anything else about SL3R, but I'll look at this other Lie group, which is also very hard to construct discrete groups, which are not lattices or like some nice surface groups. So I'll always denote by H this Lie group. Okay. So one can ask a similar question. So does there exist a discrete embedding of phi1 S, free product Z, inside this group H? Okay. There are a lot of surface groups inside SL2R times SL2R, but the question is whether one can find such a group which can be extended by taking a free factor. Okay, so here is a definition which is relevant to this particular question. So so a discrete subgroup am I writing big enough? Okay. A discrete subgroup of H is called irreducible if so I have a discrete subgroup gamma inside H and H has this splitting as like two as a product of two groups. So let's call the first one H1 and let's call this one H2. Okay. So a discrete subgroup is called irreducible if the projection to both factors are dense. Now, why is this relevant to this question? One can actually show that, well, if we have some examples like this here, then it has to be an irreducible discrete subgroup. It is a bit kind of argument, but it's true. Okay. So here are some examples. So for example, one can look at this group SL2Z at the square root of 2. So if we think this group inside SL2R, it's not discrete, it's dense. But we can embed this in H in the following way. So in the first factor, it will be identity. And in the second factor, we'll apply some automorphism of Q adjoint square root of 2. So there is only one non-trivial one which sends square root of 2 to minus. So it's the conjugate. Okay. Yeah. So now this fact that okay, it's not hard to see that this is discrete. It's also a lattice. Yeah. So the image is a lattice in H. And as far as we know, like all known examples of irreducible discrete group in H are lattices. Any question? Okay. So if we go to the first question, I mean, I don't know the complete answer to it, but here is a result that we prove, which is a joint work with Sebastian Guttraden, and it gives a partial answer, kind of negative answer to that question. So let me set some notation. So you're looking at this group H, which is SL2R times SL2R, and this is direct product of two groups, H1 times H2. And what we can do, we can embed SL2R diagonally inside this direct product. Okay? So an element is mapped to. Okay. So let's call this embedding delta. Delta will denote this diagonally. Okay. Okay. So suppose suppose sigma is a lattice in SL2R. For example, it can be the fundamental group. We can take sigma to be the fundamental group of a closed hyperbolizable surface. So you are assuming that it's a lattice. And let gamma inside H be an infinite order element. Okay, so here's a kind of cartoon. So H is product of two factors, H1 and H2, both are isomorphic to SL2R. And inside this group, we have this diagonal. And inside this diagonal, we pick a lattice. Okay, so these are sigma. And then we are picking any element in H arbitrarily, which is infinite order. Okay. So then the conclusion is that that we can look at this natural homomorphism. So which is given by, okay, so this one is sent to itself, and this one is embedded as a diagonal. Okay, this makes sense? This homomorphism cannot be, maybe I should put delta here to emphasize that it's diagonal. So this cannot be at the same time discrete and faithful. Okay. So in particular, I mean, if we have examples like that, then pi1 is cannot be sitting inside a diagonal copy of SL2R. This makes sense? Okay. Any question? Okay. So I'd like to give a sketch of the proof of this theorem. This board might not be very visible, is it? Maybe I go to that. Okay. So we'll assume that this is false. So suppose, I mean, we have examples where it is discrete and faithful. Okay. So the idea is to construct a representation of this image of this group. Okay, so in the following way. So So first, let rho from okay, we can always assume passing to finite index subgroup that this is torsion free, just to avoid issues. Okay, so say we have a homomorphism of sigma inside SL2Z, whose image is like bit large, so with non-elementary image. For example, one can choose like first a homomorphism from this to a free group and then put it inside this. Okay, so this makes sense that we can do this. Okay. Okay. So now what we can do? We can so this group lies in SL2Q, and then we can choose a different completion of Q. So let P be any prime number. So we can look at the periodic completion of Q. Okay. So we are viewing this group inside this one. Okay. Now, yeah, now the main point in here is that this group lies in a compact subgroup. Okay. So now if we look at so this group also has a nice kind of tree attached to it, which can be thought as the hyperbolic plane analog of SL2R. So this group acts on a P+1 regular tree. So maybe let's say P is 2. So there is a 3 regular tree where this group acts by isometries. And so it's a fact that there are actually 2 orbits of like this vertices. Okay. Okay. Anyway, so what we know is that this image destabilizes a vertex. So small. So rho of sigma. This fixes some vertex here. So let's call it X. Okay. Okay. This looks okay.
So this representation is not feasible.
This representation might not be faithful, yeah. I mean, we can just choose any. Okay, before using that word, okay. So now we wanted to find a homomorphism from the image of this group, and we are assuming that the image is free product of like Z and this group, right? So you can just basically pick any image of this guy here, and that will give me a homomorphism, because we are assuming it's a free product. There are no relations. So extend rho to the image of which we assumed the image is like isomorphic to this, right? Okay, so by sending this element freely anywhere. So we'll pick a specific element here. So you want to find an hyperbolic element in this group. So this element will kind of act on the tree. It will have an axis, and it will translate along that axis. Okay. So by sending gamma to a hyperbolic element.
Can you just explain, so are you extending rho to the free product with the surface or to phi of the free product with the surface? And if so, what
Yeah, so I think maybe I'm identifying a lot of things. So, okay, it's good.
I mean, it's just an action of that group, isn't it?
It's the action of the image, because we are assuming that it's a free product, right? So
The phi's in, I just don't know what phi's
No, we are assuming that it's discrete and faithful. So it's a faithful. Is that what you asked?
So they're the same group, right? I mean, this,
It's the same group, yeah, in the image.
so this is nothing to do with SL2R cross SL2R, this is just actual that.
Yeah, it has nothing to do with this.
So if you deleted 5, it's still in the same situation, is that right?
Yeah, I think we just find somehow. It has nothing to do with the specific group.
Okay.
Yeah.
Still don't know.
Yeah. We just wanted to kind of know, well, I mean, we can, for example, do this. Right? We can.
So just to be clear, 5 has so far played no role in itself.
No.
Okay.
But it will eventually. Yeah. Okay. So now here's a consequence of choosing this nice hyperbolic element is that the image. Maybe let me just write image of 5. Okay. So this has no invariant probability measure on the boundary of the tree. T is that tree, and there is a boundary. Okay. Now, why is that? Well, first of all, I mean, we have this hyperbolic element. If we think about the dynamics of this hyperbolic element, so there is like a repelling fixed point on the boundary, and there is an attracting fixed point on the boundary. And the action of the rest of the boundary is like, if you take any compact set which is discerned from this one, it will be dragged to this one, right? So using this, you can kind of show, well, any probability measure must be, any disinvariant probability measure must be supported on the union of these 2 points, right? On the other hand, we also assume that this group is kind of, the image is a non-elementary group. So this image, it cannot fix these points. It will kind of have some non-trivial action on this point. Okay. So it tells us, well, okay, so by looking at this element, we know the support must be these 2 points, but looking at this element, we find more points in the support, so it's a problem, right? Okay. But what we can do, we can construct an invariant measure to get the contradiction. Okay. Okay. So first of all, so there is a theorem, there is a lemma of Furstenberg. It says that in this situation, okay, so we are going to look at this diagonal group inside SL2R times SL2R. And the point here is that this diagonal group will act ergodically on the boundary times boundary. So the boundary of the hyperbolic plane is the circle. So it's like circle times circle. Okay. So Furstenberg, this claim is that there exists a gamma equivariant measurable map from the space of, so gamma is acting on the boundary of the tree. It's a compact metrizable space. So we have an equivariant map from from S1 times S1 to the space of probability measures on the boundary of the tree. Okay. Gamma also acts ergodically because it contains this group, right? And the subgroup acts ergodically. Is it okay?
Gamma is a free product.
Yeah, gamma is a free product, but yeah, since it contains this group, right, this acts ergodically on circle tensor.
So if equivariant with respect to this row that you just...
Yeah, I mean, yeah, I think equivariant with respect to, right. So we are viewing gamma actually as a subgroup of SL2R times SL2R by this embedding phi, which we want to show that they don't exist. And then we have a equivariant map from that group so now, now SL2QP that acts here, okay, so it's equivariant with respect to that. Okay. Okay, so what we want to do, we want to show that it's essentially constant. So maybe let's call it psi, so that meaning like we can find a point here whose kind of preimage is almost all of it. Okay. Okay. So if we can show that, then this image, this measure that we get, that will be invariant. Okay. Okay. Now, we have seen here that this group is acting ergodically here, and the same is true. So, if sigma prime is any finite index subgroup of sigma, then also this acts ergodically. The simple reason is that it's again another lattice. Okay. It's a finite index subgroup. Okay. So now we are going to look at the tree. So maybe let's draw. So we assume that sigma stabilizes this vertex. Okay. So let's consider the ball of radius n, where n is in natural number, with respect to x. Okay, in this tree. And let gamma n be the finite index subgroup of gamma, such that gamma n fixes the ball pointwise. We already know that gamma n fixes the vertex, but if we can kind of look at a large ball, then we can also pass to a finite index subgroup, which will stabilize every point in that ball. Okay. Hmm? Sorry, I meant to say sigma, right? Maybe there's a delta sigma n. Okay. Okay. Now, what the boundary of the ball looks like? So there is a boundary at infinity, which is a Cantor set, and the boundary of this ball for n very, very large, it kind of closely approximates that boundary at infinity, right? So if we look at the action of this group on the actual boundary, we know like here every point is fixed. So on the actual boundary, the action looks almost constant, like almost. Yeah, so this action on the boundary of the tree is close to the identity map on the boundary. This makes sense because, I mean, when we look at very, very large ball, then the boundary is like stabilized fully, right? So if we look at, for example, some point here, and if we apply an element of sigma n, this point cannot, for example, go here. This can kind of only stay this branch here, right? Okay, so now this map obviously is also the sigma n equivariant. So if we, for example, if we expected this map not to be a constant map, then we can kind of think about the space of probability measures on the boundary. So you can find like some compact sets which are disjoint, right? Such that the pre-image of this in Z mod, sorry, in S1 times S1 will have will not be null. Okay? But when we look at the action of this group, so since this is almost identity map on the boundary, it is also almost identity map on the probability measures, right? So if we look at the sigma n orbit of these sets for very, very large n, this will not go too far away from this set, and this orbit will also not go too far away from this set. Okay. Now these are okay. So now what we have, we can look at the p-image of these two sets, and since the full orbit of sigma n and sigma n also acts ergodically on S1 times S1, we can see, well, we are constructing two sets which are not null. Okay, so. But then this violates ergodicity because this acts ergodically on this one. So you cannot have invariant sets which are positive measures. Okay. Any question? Okay.
So the discrete faithfulness was used here in the first map.
Yes, yes. So we wanted to see, like, okay, this acts pretty nicely on the boundary.
So you say your free product element doesn't play a role?
Yeah, it plays some role. It plays to show, okay, that we cannot have these ones, right? We cannot have invariant measures.
But it hasn't played a role.
In this one, no. In this one, no. Yeah, in this one, we only needed to know that the smaller group that we have act ergodically, which is sigma. Okay.
Can you explain again why these sets are invalid?
Yeah, I kind of waved my hand a little bit. So I think it's kind of easy to, although this will not happen, suppose like you have two invariant measures. Okay. Now if we look at the orbit of this invariant, okay, maybe let's call mu1 and mu2. If we look at the sigma n orbit of this one and sigma n orbit of this one, so these two orbits will be, like for very large n, these two will be kind of far because sigma n is almost the identity map on the space of probability measures. So it's kind of like some small sets around this. Okay. Now, if we can pull back these two, and since we are looking at the whole orbit of it, the pullback of this one will be invariant by sigma n, right? So,
Your first statement, is that gamma or is it sigma?
yeah, we can put sigma here, but it's like essentially any, yeah, whenever we have. I can explain if this was not clear. Maybe after that. Okay. All right. Okay.
Sigma is not enough. I mean, 1 sigma times
Gamma is the one that doesn't have
Sigma is not enough, right?
I mean, at the end you want to say that this map is constant and so you have an invariant.
Yeah, so we have this map from here to here. I mean, it's gamma invariant, sigma invariant, any subgroup of gamma invariant.
gamma is?
Gamma is the image. Sorry, I don't know what is. Okay, so the image of this is gamma. Sorry. Okay, it's invariant under any subgroup.
Does this argument show that any subgroup containing this diagonal acts with a fixed point on the tree? Any action on a tree with a fixed point in the tree or in the bound?
I mean, we are assuming, for example, discreteness pretty heavily. Yeah, I think what if you put the right conditions, then yes. Okay. Okay. So this same idea kind of can be used to show the following. So suppose I'll try to be more consistent with the notation. Okay, so suppose gamma in SL2R times SL2R be a discrete subgroup. Let's say finitely generated. Which acts, let's call it sigma to be consistent with that. Okay, and let's say that this acts on this one, S1 times S1, what we call strongly ergodically. So by strongly, I mean any finite index subgroup of sigma will also act ergodically on the boundary. Okay. Okay. No, I think I want to change the phrasing. So, okay. So suppose that this is an irreducible discrete subgroup. Maybe instead of a statement, let me put a question. Does this group act strongly ergodically on the boundary? Meaning any finite index subgroup will also be ergodic. Okay. I mean, this is clearly true when this is an irreducible lattice or any lattice, right? But the question is, if you take any irreducible discrete group, will it always act strongly ergodically on the boundary? Okay, so I don't know the answer to this question, but using the same strategy, one can show the following. That suppose we know this is true. Then we have the following. So the first one is that no irreducible discrete subgroup of this group can be Gromov hyperbolic. I mean, I'm excluding virtually easy, okay? I mean, non-limited. So in particular, if you know the answer is positive, then you cannot have a free group which is irreducible and discrete in this group. Okay, this is an open problem like for a long time. This statement makes sense? There is no discrete and faithful embedding of, or the fundamental group of a closed hyperbolic 3 manifold to SL2R times SL2R. Okay, so closed. Surprisingly, this is also, I think, not known. If you have a closed fundamental group of a closed hyperbolic manifold, can you put it discretely inside this? Okay. So if we know, I mean, there is a big if, like, if we know this is positive, then one has this consequence. And the idea is kind of the same. So using like this, I mean, if we have an irreducible discrete subgroup, you can always find a free group inside it, which is irreducible. And then one kind of repeats the same argument. Okay. Any question? Okay, so going back to that question I mentioned at the beginning, can you find this discrete and faithful embedding of this inside H? Okay, so we at least ruled out some kind of small set of possibilities that when this lies as a lattice inside a diagonal group, then you cannot have this. But then one can ask, well, what if it does not lie in a diagonal? I think one possibility is the following. So suppose, so here is a notation. So from now on, okay, I think I have always been assuming that it's closed. Okay. So suppose suppose we have a torsion-free uniform lattice in SL2R. So this is a closed surface group. And suppose we perturb this representation. So suppose rho prime, I didn't use rho to denote anything. So let rho be another embedding of this inside SL2R, which is a lattice embedding, so it is discrete and faithful. Okay. So one can consider the graph of these two representation. One is for inclusion, and other one is this other one. So we can consider the embedding of sigma inside. So these are inside SL2R times SL2R. So the first factor times the second factor. The first. Okay. So this map is going to be the graph of these two representations. So the first one is the identity. This is just the inclusion. And the second one is rho. Now this gives a discrete and faithful representation of the surface group, right? It's clear. Okay. Now, okay. Now this representation will lie in the diagonal or a conjugate of the diagonal if I don't know why. Okay, maybe let's call it phi. If this representation extends to SL2R. Okay. So one can ask, well, if we look at this discrete group, which is a surface group in SL2R times SL2R, does it also act ergodically on the boundary? And So and the motivation is like, it's kind of what we did before. I mean, if we know this acts ergodically, then one can show that you cannot extend it to a free product, right? Okay. So here's a theorem. That this image this acts ergodically if and only if the image lies in the diagonal. So okay. Make sense? Okay, I also wanted to give a case of this proof of this, but I don't think I have time. So maybe let's point out that, well, kind of to apply the same strategy, when we make perturbation of this diagonal lattice, this strategy at least will not work. Okay, because we know that when you perturb and it doesn't lie in a copy of SL2R, then you don't have ergodic action. Okay? And by ergodic, I always mean with respect to the Leibniz measure. Okay, but here is a consequence of this theorem, which is kind of nice. So there is this question of Lyons and Sullivan. Yeah. It asks the following. So suppose M1 and M2 are two quasi-isometric Riemannian manifolds. Such that M1 is Liouville. So this means that all bounded harmonic functions M1 are constant. So it doesn't have like any interesting bounded harmonic functions. So suppose that M1 is Liouville, does it imply M2 is also Liouville? Yeah, so okay. So this, there are like analogs of these questions in other type of like spaces, graphs, and there are counterexamples. So this was like 1984, but then there was a counterexample which Lyons constructed. It's like some infinite genus surface. The fundamental group is like free, and it is also infinitely generated. Okay, but this theorem gives also examples which are nicer than that. So here is a corollary of that theorem, is that if we look at the locally symmetric space, so H2 times H2 is the space where SL2R times SL2R acts, and then we quotient by a diagonal lattice, so this one. So this is Liouville. The reason is that this acts ergodically on the boundary, but if we make a perturbation of this representation to make it a jurisprudence representation, yeah, let's say where and each factors are Fuchsians. Then we know that this group does not act ergodically on the boundary, so this has like interesting harmonic functions. And one can kind of make some argument while these two are also quasi-isometric. So this gives counterexamples whose fundamental groups are very, very nice surface groups. Okay, I'll stop here. Any questions?
So when you say extends to SL2R, so I mean this for instance includes if O is just decomposing the embedding of sigma with an outer automorphism of sigma?
Yeah, any automorphism of SL2R. Outer automorphism of so we are thinking sigma as a group inside SL2R.
Yeah, let's say it's
and
free, right? It's
yeah.
Free like
yeah.
And now you just decompose the embedding with an automorphism.
With an automorphism of sigma. I would say that this is not extending it, but why is that true? Yeah, I think it should not extend, but so we are thinking sigma is a concrete subgroup, right? If we apply outer automorphism, so the generator will go to somewhere else. Then you're precomposing with some non-trivial map. I mean, I think, yeah, more or less, right? I mean, what is the outer automorphism group of SL2R? Is it trivial? Then yes, yeah. Yeah.
I have a small comment.
Yeah.
There exists a notion of strong ergodicity, which I think has, which is not equivalent to what you're saying.
Could you repeat one more time?
So there exists already a notion of strong ergodicity that has to be almost defined subset.
Oh, okay. Then maybe we should call something else. Okay. Yeah.
Just a remark.
Okay, so maybe we should call something else. And what was the? Yeah, I think, for example, if you look at this Beatrice's question, like if you look at the reflection of the hyperbolic plane with respect to geodesic, so this should not be a conjugate. Yeah, this is the only exception. Yeah. There is always this kind of small issues.
Okay, if there are no more questions, we will resume in 5 minutes, I guess, and I'll speak again.